So yesterday we have seen, I introduced this basic definition. So if start from some Euclidean lattice, so from a more fancy point of view, it is the same thing as an Hermitian vector bundle over spec Z. And to any such Euclidean lattice, one may attach each theta invariant defined as the logarithm of the theta series, sum over exponential minus pi norm of V square. So the basic idea is that it is a counterpart in Arakelov geometry of the dimension of a space of sections of a vector bundle over projective curves in the function field case. So if you want, you may consider this as some kind of dimension over some field that doesn't really exist of some space over spec Z bar, some compactification of spec Z of E hat. So the point is that we don't really know what is the precise meaning of F1 or of this space of section, but we definitely know the meaning of the whole thing, the dimension. It is this very specific real number. Okay, so today I would like to explain three things. First of all, I would like to explain how this formalism extends to the situation where you replace spec Z by some general, say, arithmetic curve that is spec OK, where OK is a ring of integers of some number field K. And then I would like to explain how this formalism of H0 theta extends to some kind of infinite rank Euclidean lattices. And finally, I would like to say a few words about applications of this formalism to Diophantine problems. Okay. So let me introduce a few notation. So K will be a number field. OK, it's a string of integers. Its degree will be denoted by capital N, and its discriminant delta K. OK. Of course, you have a ring morphism from Z to OK that geometrically may be understood as a morphism from spec OK to spec Z. And this morphism has a relative dualizing sheaf, dualizing module. That seems something quite classical. You may consider the morphism of Z module from OK to Z. And it's actually some OK module by composing by internal multiplication. And actually, this OK module, it's the classical inverse of the different. It's an invertible sheaf. It's a rank 1 projective OK module. And it has a natural version in Arakelov geometry. So in Arakelov geometry, an Hermitian vector bundle over spec OK will be given by some projective finite rank, projective finitely generated OK module. So it's the same thing as a finitely generated torsion-free OK module on a family indexed by the field embedding of from K in C of Hermitian metric on E sigma, the complex vector spaces you get by base change from OK to C by the various field embedding. And this data is supposed to be invariant under complex conjugation. So basic notion in Arakelov geometry. And in that case, there is a very natural metric on the dualizing bond sheaf. Namely, you have a canonical element in this dualizing sheaf, the trace. And you impose the norm of the trace at every place to be 1. Okay. And now I will be interested in defining some general theta for some general Hermitian vector bundle like here. So E is some projective OK module of finite rank. And at every place you are given a metric. Okay, now in this situation, from this projective, this Hermitian vector bundle over spec OK, you may construct some Hermitian lattice over spec Z by the Arakelov version of the classical construction of direct image. So you may consider as direct image, it will be some Euclidean lattice, some Hermitian vector bundle over spec Z, a Euclidean lattice. And by the very definition, the Z module underlying the direct image is the original module itself, but seen as a Z module. And one also has to define the metric on the direct image, and to define the metric, the Euclidean metric, by taking the sum of the squares of the various metrics. Okay. So that's something indeed quite familiar in geometry of number. For instance, if you start with OK itself with a trivial metric, you get some classical Euclidean lattice that is a usual lattice associated to a number field when you prove basic theorems about units in number fields and so on. And actually, it's very easy to compute the Arakelov degree, the covolume, equivalently, of this direct image. It is the same as the Arakelov degree of the given Hermitian vector bundle. So this Arakelov degree, maybe I should remind the definition. You take the maximum exterior power, so you are reduced to the case of a line bundle, and in that case, you take any element alpha non-zero there, and you take the log. It's a classical notion of degree. I suppose you have met in Christoph's lectures. So alpha is an element there. Okay. And you see an additive correction which involves the log of the discriminant that corresponds precisely to the fact that basically the discriminant is a square of the covolume of the lattice defined by OK in the usual way. Okay, so you have this formula that is a very classical formula, and you also have a duality formula. You know that the direct image, the dual of the direct image, is a direct image of E dual twisted by the inverse of the different. It's a basic formula when you study invariance of number fields, and actually this isomorphism is compatible with the metrics as they have been defined before. And you get this formula, which actually is a very old formula. In the case of Hermitian line bundle, it goes back to Ansel. It has 1 century now. Okay. Okay, this formula have basically to do only with Arakelov degree. And actually, they lead naturally to the following definition. Okay, something I should also add. The degree of this relative dosing sheaf is the log of delta k. So in formula related to, involving number field, the log of delta k plays the same role as 2g minus 2 in algebraic in the function in the geometric case when you work over a curve of genus G. Okay. Now, it's quite natural, if you mimic the geometric situation, to define H0 theta of E bar as, in the general case, over spec OK, as H0 theta of its direct image. If you are in the geometric situation, it's tautological. Okay. And it's also quite natural to define some H1 as H1 of the direct image, and H1 for an Hermitian vector bundle over spec Z. For a Euclidean lattice, basically you have no choice because of Poisson formula. You want to have, you are directly led to define H1 as H0 of the dual. So at the end, altogether, you get these definitions for H0 theta and H1 theta of any Hermitian vector bundle over an arithmetic curve. And now, the previous formula concerning the degree and so on, and the Poisson-Riemann-Rohr formula over spec Z I explained yesterday, fit together and give you this more general Poisson-Riemann-Rohr formula. H0 minus H1 is the degree plus the rank times something that plays the role exactly of 1 minus G. Okay. Okay. And moreover, the Landsberg-Ansel duality formula tells you that H1 is H0 of A dual tensor omega in this metric world. Okay. And now it's quite formal to extend many results I explained yesterday to this more general framework by using this basic property of direct images. For instance, the H0, H1 of a direct sum are the sum of the H0, H1s. And you get some subadditivity for short exact sequences in this more general case, and so on. Now I would like to discuss in more detail something that is rather trivial over spec Z, namely what is H0 theta for an Hermitian line bundle over a general arithmetic curve. So you remember, in the classical case, if you are interested in H0 dimension of space of section of a line bundle over a compact Riemann surface, it's a very old story. And basically, the last result to prove is the Riemann-Rohr formula. Actually, Riemann did not prove Riemann-Rohr. He had only an inequality. And the very basic result is basically has no name, as it is quite trivial. It is a result that tells you that if you take L a line bundle, over a smooth projective reducible curve, if the degree is non-negative, the dimension of H0 is at most 1 plus the degree. It's clear by looking at the jets of order 1 plus degree at any given point. So this estimate is so trivial that it has no name in the literature. And it's basically the starting the estimate you start from in Riemann's analysis on proof of Riemann-Roch. So in the arithmetic case, we will get similar formula, but the proof goes in the reverse order. You start with Riemann-Roch when you do various things, and at the end you get the most trivial inequality. Okay, so here is a proposition that summarizes many results from van der Heer and Groenewegen and myself. So it's possible to prove that if you take any Hermitian line bundle over spec OK, when the degree is non-negative, then you have an estimate similar. This estimate is still true in the Rakelov world. Actually, you have some constant c at the nth power that becomes actually very, very small for when you work over a number field of large degree. Okay, so this is requires some work, but it's quite familiar. And in application, you have really 1 plus degree if you want. I don't know any application where this more precise result we see at the end is really useful. Okay, and now, of course, the other very basic estimate in the geometric case is that when the degree is negative, this dimension is 0. And this, of course, cannot be true as such in the arithmetic case, because the only Euclidean lattice with 0 H0 theta is a trivial Euclidean lattice of rank 0. You always have a little bit of sections. So, of course, the direct image has never rank 0, so it cannot be true. But this statement tells you that, okay, it's not true, but it's almost true. This is very, very, very small. So it's something that is doubly exponential, which goes to 0 doubly exponentially in the degree. So you see when the degree is negative, this minus thing is positive. So you take the exponential of this thing, which is positive, and you take exponential of minus this thing. So it's incredibly small. And here again, this implies some exponentially small estimate with only one level of exponentials that in applications is quite good enough for anything I know. So these results are unexpectedly close to the one in the geometric situation. You cannot have 0, but you have something very, very, very small. Okay, I did write what I just explained there. But to prove this, I don't want to say too much about the details. What is very funny is that you start from Poisson, Riemann-Roch. And you add the end by adding some, more or less elementary arguments from geometry of number, you get these estimates. Okay, now I would like to turn to the key point of this lecture. I would like to say something about infinite rank Euclidean lattices. So first of all, I would like to introduce some definition. This definition is, okay, you have to believe me for a few minutes without motivation, and I will give the motivations later on. Okay, so actually there are various kinds of infinite rank Euclidean lattices. The pro-infinite rank Euclidean lattices on the end. Some are defined as projective limit, other one as inductive limit. So in this talk, I will focus on pro-infinite rank Euclidean lattices, and they may be defined as follows. It will be a data of 3 things. First thing, E hat will be a Z module that will be equipped with some topology, and which, as a topological Z module, is isomorphic to Z at the power n. Space of sequences of integers equipped with a product topology, the topology of pointwise convergences of sequences. So it's a very big space. It's not a locally compact space. It's a large, complete, Polish space. Okay. Second part of the data is some real Hilbert space. And the third part of the data is some kind of comparison map, I, that embeds the real Hilbert space inside the real topological vector space you get by taking the completed tensor product with R of E hat. So once you have identified E hat with Z at the power n, this topological tensor product is nothing but R at the power n with a pointwise convergence topology too. And you require this map I to be linear, continuous, injective with dense image. So you see, it means that inside this space of sequence, you have a slightly smaller space that is an Hilbert space, and that is dense. So you have some kind of, you can think of this as some kind of extended Hilbert norm of Rn that will be finite on this subspace and will take the value plus infinity elsewhere, if you want. Oh, yes, it's, yes. I have switched, it's, yes, the Z on the R. Thank you. Okay. Okay. So you see, the first and the second part of the data, you cannot directly compare this Hilbert space on E hat. E hat is not embedded in this Hilbert space, but both live in this real, larger real vector space. So you have to compare this picture to the one for a Euclidean lattice. A Euclidean lattice, you have some E inside here on a norm. You don't distinguish between a small real vector space and a large real vector space. But here you have to. Okay, let me give you a few examples. First example, that could be called some kind of arithmetic Hardy spaces. So you chase some positive real number R, and as E hat, we may choose the space of formal series in one variable with Z coefficients. So in this case, of course, when you take the topological tensor product with R, you get the real formal series with in one indeterminate with the topology of pointwise convergence of the coefficients. Okay. And you may define some natural subspace that will have a natural Hilbert space structure by imposing some convergence, some L2 convergence condition on the coefficients of a series. Okay. For instance, I can consider these conditions. Sigma of the square of the modulus of the n, R to n, is convergent. And of course, this condition exactly means that the series defined, the sigma of n Zn is analytic in the open disk of radius R, and also it belongs to some Hardy space. Okay, it means that if you look at the L2 norm on a circle of radius little r, this L2 norm stays bounded when R goes to the capital R. So this, you may identify such a space as a space of L2 function on the circle of radius R that are boundary values of holomorphic function inside the circle. Okay. So this data defines some object in a new category. You have some formal part, E hat, some Hilbert space, and of course the Hilbert space is by definition embedded in the real formal part, E bar R. So I did write here a very small observation. This infinite rank Euclidean lattices really depend on the choice of R. For instance, when R is large, is at least 1, it's very easy to see that the only formal series that is L2 on this disk of radius larger than 1, at least 1 has to be a polynomial. But when R is small, this intersection is very, very large, is uncountable. So there are many ways to see that. But these objects are quite general and basically impossible to classify. Okay, this is the first example. Now let me turn to another example. It's quite easy to construct infinite rank Euclidean lattices starting from a projective system of Euclidean lattices. Assume that you are given such a system. So A0 hat is a Euclidean lattice, A0 bar is a Euclidean lattice, E1 bar is another Euclidean lattice, and you have a map which is admissible in the sense that it's surjective at the level of the module, and the norm on E0 hat is a quotient of the norm on E1 on E0 bar is a quotient of the norm on E1 bar, and so on. So here you have a projective systems, both in the category of Z modules of finite rank and in the category of, let's say, Euclidean spaces. Okay. So if you are given such a gadget, you may define a kind of projective limit that will be an object of this new type. And indeed, its formal part, E bar, will be the projective limit in the usual sense of the Z modules. So by definition, an element of the projective limit is a sequence of elements xi's in EI, that are compatible with the map in the system. Each one projects onto the previous one. And of course, if you take the topological product, tensor product with R of this projective limit, you get the projective limit of the underlying real vector spaces, systems of vector or sequences of xi's with xi's in EIR that are compatible with the system of maps. But you may observe that as on every EIR, you are given some Euclidean norm, because they belong to some lattice. Inside this projective limit, you may consider a subspace. The subspace of sequences such that the sequence of the norms of the element of the sequence, this sequence by definition is non-decreasing because the element projects onto each other. And you may ask this sequence to be bounded, or to have some limit. And this is some kind of projective limit, if you want, in the category of norm vector space where the morphism have to decrease the norm. And it's very easy to check that it is some Hilbert space, that which by definition is included there. And it's very easy to check that this inclusion is dense. The point is that, of course, if you take any point xi in some EIR, you can find some element in this Hilbert space that maps onto it. You have only to lift at every time with the element of shortest norm, taking the orthogonal projections with respect to the kernel. So this is a typical example of our gadget. And actually, it's very easy to check that this is not only an example, but any infinite rank Euclidean lattice as defined initially may be realized in this way. It's very easy. But a very tricky point is that if you want to extend the definition of the theta invariant to this infinite rank objects by taking some limit, it's not formal. It's very easy to see that the asymptotic behavior of H0 theta of EIs depends of the choice of the projective systems from which you construct your projective limit. It's definitely not something intrinsic. And it's very remarkable that it is possible to find a class of infinite rank Euclidean lattices for which there is a nice theory of H0 theta. So that's something I would like to explain. The point is that for any Hermitian infinite rank Euclidean lattice as above, you may try to associate intrinsically defined H0 theta invariant. And for instance, there is an obvious candidate that will be to copy this formula. But of course, you have to consider element in the, let's say, integral part. You only consider the element for which the Euclidean norm is defined. So you have to deal with this intersection. But this definition is quite strange because, as I mentioned before, there are many cases where this intersection is uncountable. So you have to exclude them for this to be finite. Okay. So in a sense, it's very easy to see that it is some kind of smallest possible candidate. If you have to. And there is also another candidate that is some kind of largest possible candidate. You consider all the projective system from which you can recover your infinite rank Euclidean lattice. For any such projective system, you may consider the sequence of the H0 theta of the element of the system. You take the, how do you say this, lim inf, and you take the inf for all the lim inf. And you get something different. It's a little bit when, as in a measure theory, once you have defined the integral of functions with a finite number of value, you can approximate in various ways general functions. Okay. And the first one is always smaller than the second one. Okay. Now, here is a main technical theorem. Assume you start with a projective system as above. And I claim that if the following summability condition is satisfied. So I have to explain what it is. So you see you have a projective system of Euclidean lattices. So you may think that at every step, when you go from EI to EI plus 1, in some way you take some extension by some kernel of QI. And this kernel of QI has a natural lattice structure. Okay. And basically, the theorem asserts that if the series of the H0 theta of these various extension steps converges, then the various candidates for H0 theta of E bar hat coincide, and actually coincide with the limit of the H0 theta of the approximations. Now, for technical reasons, it's not sufficient. Well, I don't think it's sufficient to assume only the convergence of the sum of the H0 theta of K QI bar. You have to slightly strengthen this condition by allowing this, by requiring the condition after a small rescaling, that increases the H0 theta. Okay. So the point of this theorem is that basically, for instance, what is, for instance, something that is easy to see is that this limit exists. It's a simple consequence of the subadditivity of okay. If you take some EIA, the subadditivity for exact sequences shows you, by using this subadditivity, you may see that the algebra theta of the big thing is that much algebra theta of the small one, plus a correction that is the sum of the algebra theta of the various layers you add. Okay. And now, from the fact that this series, the series sum of all the K algebra theta of K converges on this infinite sequence of inequality, you get that this limit exists. Okay. And now, to prove that the other equality, you have to do some much more serious work. And actually, in a sense, so maybe the most basic thing you have to recall concerning this theorem is that it is related with that kind of subadditivity. And the very point is that in this subadditivity estimate, you don't have any constant that involves the rank of the vector bundles of the lattices. So that's the key point I did emphasize yesterday. You have a theory of invariant in geometry of number where you have a lot of estimates that never involve rank of the vector bundles. So if they don't involve the rank of the vector bundle, you can let the rank goes to infinity. So that is the basic philosophy, and this is a more precise theorem. And actually, it's possible to prove that this result is basically optimal. That, namely, whenever you have a Euclidean lattice for which the two candidates for algebra theta coincide, then they may be constructed as a projective limit that satisfy basically the same convergence condition. Okay. Maybe I will not spend too much time about discussing the proof of this theorem. So it's really basically a theorem in analysis, which combines several of the ideas I mentioned yesterday. It's deeply related with the subadditivity of the algebra theta, and it also has a lot to do with this whole construction of Banachik. If you have a Euclidean lattice, you may associate to it some natural measure of the total mass of the Banachik measure will be the exponential of H0 theta. So that's a measure you get by giving some Gaussian weight to every point of the lattice. And technically, that kind of summability condition concerning the series allows you to prove that this Banachik measure has a very nice, let's say, asymptotic behavior. Namely, so you have to write this. So this is the map, projective map, PIG. So for every of these lattices, you get a Banachik measure. if you have a measure there on EJ, you may consider its direct image by this map. So if you fix I, and if you let j goes to infinity, you get a sequence of direct image of the Banachik measure on this space. And the point is that the summability condition on the various on the H0 theta of the various additional layers allows you to prove that this sequence of measure has a limit, has a measure on this big countable space. So that's the first part of the construction. And now, for every I, you get a measure mu I by this limit process. And now this measure are compatible. If you take the direct image by Pij of mu j, you get, by the very definition, mu I. So you get families of measures that are compatible on this projective system of countable set. And now well, maybe it's a not too difficult, but remarkably deep result of Kolmogorov that the functor limit projective limit commutes with the functor measure. It's in his book, Grundbegriffe der Wahrscheinlichkeitstheorie, maybe that's the main new result. He constructs measure on infinite products. The key idea in probability. So the point is that in this situation, let's say, you work with sensible spaces, Polish spaces here. If you are given a measure on this big space, you may consider its direct image at each of its finite level approximation EI. And the map that associates to a positive measure of finite mass on this limit, this compatible system of measure at each step is a bijection. So it means that in this situation, this family of measure may be seen as a measure on this big space that is not countable at all, of course, E hat. And now it turns out that, okay, under the stronger summability condition, you may prove that this limit measure is a naive version of the Banachik measure on the big space given by this series. So this is basically a lot of estimates that involve at many places concavity or convexity properties of Gaussian sums and so on. But basically, it's the fact that the various candidates for H0 theta in such a case coincide is some kind of tameness results about some limit measure. Okay. So here, even if you are, well, it's quite, even if you are interested, well, only in the final result, for the proof on the final result doesn't involve at all the definition of the Banachik measure. Quite clearly, the Banachik measure is a key tool behind the result, the key concept. Okay. Now I would like to explain how you may use this gadget to do some Diophantine geometry. Okay, I would like to focus on some very concrete Diophantine results that, okay, basically it is due to Chudnovsky, on which in a way goes back to very old theorem of Émile Borel. So maybe you know this theorem of Émile Borel that tells you if you take f F a formal series with Z coefficients that have a positive radius of or complex radius of curvature, and that is meromorphic on some disk of radius larger than 1, then F is a series of a rational function. Some kind of algebraization statement that tells you that, okay, if you have something that is both formal object defined over the integers that satisfies some analytic condition over something, some sufficiently large domain, it has to be algebraic. Here it's more than algebraic, it's rational. But actually it's very easy to see. If you know that F is algebraic, the conclusion is very easy. Okay. So let me explain some much more modern version of this due to Chudnovsky in a way. So let me consider the following data. So I consider families of formal series, phi, n of them, with Z coefficients. So I want to see this, to understand this as some kind of, as giving you some germ of formal curve in the projective space over Z. So your germ of formal curve, so if you want, with something like spec, whatever it means, to Pn. Well, actually it goes to the affine space. Now, for instance, here you have the scheme of definition. Let's call it 0. So it sends 0 to phi of 0. That is a point in the projective space I can see as a point in the complex space. So you can consider P, the origin of this formal curve, and also its derivative that I assume to be non-zero. So if you want, it's a way to describe a smooth formal germ of formal curve into the projective space, if it is not zero. Okay, the other part of data I consider is a connected compact Riemann surface with boundary on some point in this Riemann surface. You have M. This is inside M, and this is the boundary of M. And now I also assume that I am given an analytic map, J, from this compact Riemann surface to the projective space over C. And this map, you want that its derivative at 0 is not 0, so it will define a smooth germ of analytic curve into P and C. And you want that this smooth germ coincide at the formal level with the image of phi. You send the formal completion to this curve inside the projective space. It has a meaning to say that this formal germ of curve defined by this analytic map coincides with the formal germ of curve defined by phi over c. So in a sense, you are given some kind of formal tube, formal arithmetic surface around spec z, embedded in Pn of z, and it is glued with some Riemann surface by some intercomplex numbers. Okay, now in this situation of a compact Riemann surface, there is a completely natural metric defined by using potential theory at the tangent space of any point inside the Riemann surface. It is a classical construction related with the construction of Green function that is explained on this picture. So you see here, so it's a purely analytic discussion. So you have a compact connected Riemann surface with boundary, and you choose a point O inside the surface. So imagine your surface is realized in gold, and you put a unit charge there. No, I should not say that. Well, if you want, you can, if you have a new charge on this two-dimensional world, you consider the potential it creates submitted to the Dirichlet condition that it is zero at the boundary. That I did right by this picture. So if you put a unit, so using current theory, it corresponds to the fact that I dd bar g0 is minus pi delta 0. And this function g0 has to be harmonic outside the point 0. It has to vanish on the boundary. This is the Dirichlet boundary condition. And the fact that you have a unit charge in this two-dimensional world tells you that g0 has a logarithmic singularity at the point 0. At the point O. So if Z is a local coordinate, holomorphic local coordinate near O, G, this Green function, is given by log of Z minus Z at 0 modulus inverse, log of R inverse, plus something that is harmonic, that is infinity near 0. Okay. And now it turns out that if you look at the additional term, you look at the contents part of this additional term, you may write it as a well-defined, as a logarithm of a well-defined norm of d over dz. So what I mean here is that if you change the, for instance, if you replace lambda by z by 2z, this constant term will be divided by 2. So at the end, it means that you have a well-defined norm, the capacitary norm, on this tangent space that makes this formula true. Okay? So what I mean is that the constant term in this expansion depends on the local coordinate, but its dependence may be written, corresponds to the fact that it may be written as minus log of some intrinsically defined norm on the tangent space of the vector d over dz. So maybe I should do the computation in the case of the disk. For instance, take M, the disk of center 0 on radius r, closed disk. Take for O the point 0. This is a 0 on O is 0. And now you have a formula, of course, for the Green function. G0 is log, is a positive part, is log of R over Z. This takes the values 0 on the boundary, and it has the right singularity at the origin. So, it's G0 of Z. So this means that the capacitary norm minus log is log R. So it means that d over dz cap 0 is 1 over R. Okay. You have some completely natural metric on the tangent space inside the surface with boundary. Okay. So, in our situation, when a formal curve is glued with such a compact Riemann surface with boundary, you get a metric on the tangent space to your formal curve. And the theorem is that if this metric gives to the natural integral tangent vector a length smaller than 1, then your formal curve is algebraic. So for instance, this here is a computation for a disk of radius r. If you subtract to your disk a finite number of very small disks, this will not be true, but almost true. When the epsilon i's are small, it's true that this capacitary metric is very close to the one you get in the situation with no hole. It's a very basic result of potential theory, the fact that points are polar. Okay. And now, for instance, you may apply this theorem to the Borel situation. In the Borel situation, you have one formal series. You may consider its graph consider phi, which is t, f of t. It's a graph of phi. If phi extends as a meromorphic function on a disk of radius more than 1, you may glue, if you want, you have it means that the graph of this formal series may be glued with the graph of phi seen as an analytic function on a disk of radius more than 1 minus small disk around points. And here, in this situation, of course, if R is larger than 1, this condition V smaller than 1 is satisfied. So you get that if R is smaller than 1, the graph of phi is algebraic. But of course, once you know that the graph of phi is algebraic, you see immediately that after multiplying by some polynomial with z coefficients, phi is holomorphic on a disk of radius more than 1, so it is a polynomial. It's very easy to conclude. Okay. So it's a typical situation of Arakelov geometry. You have a combination of integral constraints formal series have to have z coefficients on some Archimedean complex analytic constraints. And actually, you can express this in terms of Arakelov degree, but maybe I should not explain this. And I would like to give some discussion on a possible approach of that kind of result. Of course, there are many classical approaches by various people, Chodnowski and Yves André and myself. And maybe before I say that, I will only say that this result in its full generality is more interesting than the whole result of Borel itself. For instance, you may apply it to elliptic curve. If you take two elliptic curves, and it was basically the idea of Chodnowski, if you have two elliptic curves over Q that have the same AP invariance for almost every P, then it's classical results in the theory of formal groups that, let's say, over spec Z1 over N, they have isomorphic formal groups. And now, it's very easy to see in that case that the graph of such an isomorphism of formal group, it will be the formal germ of some kind of analytic Lie group that will extend to some very large Riemann surface with boundary, and the algebraicity condition is satisfied. So it's very easy to see that the graph of such an isomorphism of formal groups, once you know that it is algebraic, it's very easy to see that it defines a Q isogeny between your two curves. So in this way, you get a special case, all theorem of Serre and Faltings did not prove it in this generality, but some result, all classical results of Serre and Faltings about the fact that the L series of an elliptic curve determines it up to isogeny. So it has a real analytic content. Okay. Now I would like to explain the basic idea behind a proof using this infinite rank Euclidean lattices or Hermitian vector bundles of such an algebraicity statement. So I suppose before I give the proof, I will give a very, very short proof of a very classical algebraicity statement, namely Chows Theorem. So on one slide, I will give you a proof. So remember that the theorem of Chows tells you that any compact complex analytic submanifold, or more generally complex analytic subspace, of the projective space is algebraic. So of course, you may see this result as a very special case of Serre's Gaga, but it was known much before Gaga, and actually Chows, of course, gave a proof, but let me give you a proof that in a sense appears in some old paper of Poincaré about abelian functions, maybe at the very end of the 19th century. So I claim that Chows theorem follows from two facts. The first fact is something of purely algebraic nature, that if you take some closed algebraic subset, there exists a line bundle L on Z, your closed algebraic subset, so that the dimension of the space of sections of this tensor power of L grows at least like D at the power dimZ. Of course, you know that. You know that O of 1 satisfies this condition. And you know that actually if you take O of 1, this becomes a polynomial, the Hilbert polynomial, when D is large. But I will use only this tiny part of this classical result. And actually, it's very easy to prove this. You can prove this at the very beginning of a course of algebraic geometry. Once you have notaire normalization, you are reduced to the case where you may replace basically Z by P at the dimension Z, and that's it. It's a very elementary result. So on the one hand, you have this lower estimate for the dimension of the space of section in the algebraic world. On the other hand, you have the following upper estimate that holds in a very general analytic setting. If you take X, a compact analytic manifold, you take any analytic line bundle, the dimension of the space of sections of this tensor power of L grows at most like D at the dimension of X. So there are many elementary proofs of this too. You can play with Schwarz lemma, but if you know a very little bit of things about positive curvent on a pluriharmonic function, it's very easy. So you have, okay, it's a very, very basic result. And now, if you combine these two results, you get very simply Chows theorem. So let me explain that. You start from X, as in the statement of the theorem, and you look at its Zariski closure. Of course, it's some algebraic variety, possibly larger, which is easily seen to be reducible if you start from something connected. And if you take any, okay, now you choose the L on the Z given by the first statement. Of course, it is O of 1, but you don't even need to know that it is O of 1. And you look at the space of section of the D power of L over Z. It's a finite dimensional space. And if you take any such section, algebraic section, of course, you may restrict it to X. It will be a nice analytic section. And by the very definition of Z as the Zariski closure of X, if S vanishes on X, it has to vanish on Z. So this map is injective. Okay? And now if you compare these two bounds on the dimension when D goes to infinity, you get that the dimension of the Zariski closure is bounded by the dimension of X. So it implies that X is a component of Z, and if you know a little bit of thing about connectivity and connexity in algebraic geometry, you are done. Okay? Okay. No, now I claim that you can give a proof of that kind of algebraicity statement a la Chudnovsky using exactly the same kind of tool. Let me explain this. So in our situation, we start with some kind of formal surface, formal spectrum of Z of t, that you glue to a Riemann surface by means of this map that embeds that in the projective space. So I don't want to be too precise, but I want to explain the idea. You have some kind of hybrid objects, that some kind of formal analytic surface you obtain by gluing this formal spectrum of Z of double bracket T on a Riemann surface. Your data tells you that this formal gadget is embedded by some formal analytic map in Pn of Z. Okay. Now you may consider some avatar of the space of sections of O of D on these objects. So I don't want to explain the formalism completely, but you may take the formal sections of the pullback O of D, so it is a space of formal series, and you may take the L2 analytic sections that constitute some Hilbert space of the section of O of D on your embedded analytic Riemann surface with boundary. And of course, these two things are compatible. You have they form together a gadget as before. If you have an L2 analytic section, you may look at its germ at the point 0, and it belongs to the complexified space of E bar D. And now the key point is that this capacitary condition implies that the H0 theta invariant of E bar D, oh, I did forget, here there is a bar, is well-defined and finite. Well-defined, I mean, you may, the various candidates for H0 theta coincide, and you may compute it by the previous theorem about converging sequence of H0 theta of the Kerr QIs. And actually, there is missing some bar. The H0 theta of this space of section of O of D, so to speak, goes like D square. On this you get, in a way, once you have the general recipe to compute or to estimate H0 theta, you have no choice. You have to compute this subquotient, the square of Qi, and you have to estimate the H0 theta of the subquotients. And to do this, you have to do a little bit of analysis, because you have to estimate norms on the subquotients of Hilbert space. And actually, it's directly related to some kind of Schwarz lemma. And then, once you have obtained some results on this metric and the degree of the subquotients, you apply the general estimates I explained before, relating H0 theta on the Arakelov degree. But you have absolutely no choice in the computation. At the end of the day, you get this upper bound. And this upper bound is really something that implies, by the same kind of argument as in Chows theorem, this plays the role of the analytic estimate in Chows theorem. And it's very easy to see that by mimicking the proof of Chows theorem, to prove that implies that the Zariski closure in Pn of Z of your germ of curve at dimension at most 2. And of course, it means that over Q, it's an algebraic curve. Okay. Now, I would like to say a few words about some other. So you see, in this situation, in a way, the key result becomes this estimate. And this estimate is quite natural. You see the dimension 2 is related with this quadratic growth of the H0 theta. Now, I would like to present you something which I find more puzzling, because we find some kind of dimension that are not integral, that occur naturally in Diophantine geometry. So that's something which I find intriguing. Okay, so I would like to explain you the theorem how it's possible to understand the classical theorem of Schneider-Lang as an algebraization theorem using the same kind of technology. Okay, so let me first recall you a statement of the theorem of Schneider-Lang. So you start with some number field that you embed in C. You have a preferred embedding of K in C. You're doing that's a transcendence theory, so you choose one embedding. So let me call it sigma 0, this embedding. Okay. Now let me consider a smooth quasi-projective variety in Pn of K. And let me assume that I have given, let's say, some ordinary differential equation. So geometrically, it corresponds to a subvector bundle of rank 1 of the tangent space of X. So X and F are algebraic and defined over K. Okay, let me also assume that the following analytic data is given. You are given a subset, closed, a locally finite subset of C, on some analytic map from the complement of delta in C to the complex analytic variety X sigma 0 you get from X by embedding K in C by the preferred embedding. So, let us assume that F is meromorphic on C of finite order. So what does it mean? So it means that, you see, once you embed X in Pn, F extends to C as a map to Pn of C. So it's a fact it is meromorphic on C. on finite order is a growth condition on f tilde at infinity. So maybe the simplest way to express finite order condition is to use a little bit of Nevad-Linear theory. And it's to say that if you take the inverse image of the Fubini study 2 form on Pn by f tilde, it doesn't grow too fast. And a way to express this growth condition is to say that the log plus of r over z, so it's supported by the disk of radius r, of this inverse image is like grows like some power of r. So for instance, if f maps to some to the affine space, this condition says that the growth of the modulus of f is something like exponential of r at the Rosse power. In the computation of this f upper star omega, there is some logarithmic derivative involved in the hidden way. And finally, I assume that f is an integral curve of our ordinary differential equations. It goes in the complex world along the leaf. Okay? Okay, so here is a geometric formulation of Schneider-Lang. So assume that there is a finite number of points in the source of f, the image of which is in the k-rational point of x. So here, of course, little f of capital F is defined in the complex world, and x of k is in the world of k points, but k is embedded once and for all in C. So it has a meaning. So the theorem of Schneider-Lang tells you that if this set of points with image in the rational point by this integral curve for foliation is large enough, and the large enough condition involves rho, the growth, the Nevad-Linear growth of f at infinity, on the degree of the number field. So when the growth is very large and the degree is very large, more general condition, you need more points. So under this condition, the image of f, that is some analytic, embedded analytic curve or something like that, is actually algebraic. So another reformulation of that is that if you know that the image is not algebraic, that is, if the Zariski closure of the image of f of your analytic curve, solution of an ordinary differential equation, is at least 2 over C, then the number of points with image in x of k is bounded by in terms of rho on the degree. So maybe the simplest example of this theorem, if you take the map that sends z to z on exponential z, and of course, it's an integral curve of a very obvious foliation on the plane. And you get that if you have a finite set in a number field, it's mapped by the exponential, a submolar field of C, that the map by the exponential map is in C. The number of points in this set is at most 3 times k over k. Because, of course, here the order of growth is 1, rho is 1. But, of course, if you have 1 point in q bar that is not 0, whose exponential is in q bar, you take multiple of these points, and we'll get counterexamples to these assertions. Okay? So this tells you that the theorem of Hermite-Lindemann is true. You have no point in q bar. Sorry? Pardon? Oh, in q bar. Oh, I'm sorry. In k, sorry. I'm sorry, it's a misprint. You're right, it's in k. Okay. So this property looks technical, but if you add 1 point in Q bar at with exponential in Q bar, by taking Q bar K large enough on a large a sequence of multiples, you will contradict that. Okay? So this, in this simplest case, is exactly the theorem of Hermite-Lindemann. Okay? Okay. So now let me explain how you can prove this, what it is in natural interpretation using this infinite rank Euclidean lattices. So here I will work with infinite rank Hermitian vector bundles over K that I did not define, but you can imagine that it exists. So basically it goes as follows. For any point in our set, you may consider its image on the formal germ of leaf of our foliation through this point. And over the complex places, you may also consider, let's say, analytic leaf. So over the given complex place, you have a very large leaf that is an entire curve, parameterized by C. And if you work at an embedding that is different of sigma 0, you may consider a small analytic disk. It exists by integrability. And in a sense, you may consider these formal curves, L alpha bar, glued together by construction with this analytic leaves, and define some kind of formal analytic space. You have the formal structure over K, and when you go to the complex fields, various complex embedding, you may glue with this analytic integral curves. And actually, you may give some kind of integral structure to the F alpha bar to give a sense to them not only over K, but over OK by using some ring of divided powers that appear naturally when you formally integrate a vector field. And now in this setting, you may consider the global sections of the pullback of the tautological line bundle O of D on the big projective space where everything takes place on this formal curve over spec K with divided power structure glued together with stupid leaves at the sigma which are not sigma 0, or with a non-trivial leaves that is given at the place sigma 0. So you may do this construction, which is a way to interpret as building some kind of hybrid objects, formal and analytic, the various data of the Schneider-Lang theorem. And you may consider, in the spirit of the previous proof of Chows theorem, the space of sections of O of D on these objects. And the space of sections have some formal parts, which correspond to sections of O of D on the formal schemes you are given. But you also have some natural Hilbert structure by looking at space of L2 homomorphic sections on the complex leaves. And in this case, you may compute the H0 theta of this big gadget, and you find that it is finite is precisely the ratio that enters into the statement of Schneider-Lang theorem is large enough. And actually, you find that it grows like some power of D with some exponent, which is what it is. This is rational, non-integral. And okay, and you may conclude the proof in the case when if this exponent is smaller than 3, then you may conclude the proof as before by comparing Hilbert polynomials. But what is quite strange is that in a sense that kind of hybrid objects that appears naturally by mixing this growth condition a la Schneider-Long with have some natural dimension which is non-integral. Okay, so let me say a few words about the proof of this. Here again, once you have defined the objects, you have basically no choice. The only way to compute the hedge theta is by using the description of this space of sections, formal analytic sections, in terms of jets at the point you are at the various point f. You have some, so to speak, tautological presentation of this Hermitian vector bundle of infinite rank as projective system in the previous sense. And if you apply the general theorem, you have to compute a theta of subquotients. And here again, to do that, you have to you are led to prove to do some analytic estimates that goes from Schwarz lemma, and then the general estimates relating a theta on degree of line bundles on some very elementary computations leads you to this computation. Okay. So I suppose it's a good point to stop.